Yeah, today we're going to discuss lab 12, which is about exhaustive search or brute force search. Now we start off with a simple example. That is, you are given a list, okay, and you want to find a particular value x, whether it exists or not. So we start with an example where you are given a list of 500 elements, and each of these elements is a random value selected in the range from 0 to 10,000. So if you remember for Python, range 0 to 10,000 means that it generates integers between 0 to 9,999 inclusive, but exclude 10,000. So which means we generated 500 elements here. There is random value and they are in this range. Okay, so if you print out the value of L, this is the list of 500 elements. Each of them is in this range here, and there are 500 of them. Okay, you don't have to know this syntax here. This is just basically generating 500 elements and random value in this range from 0 to 10,000, but not including the 10,000 itself, right? So this will not be tested. This is just for experiment purpose where you are given 500 random values and you are asked to find x, which are initialized to 13. Okay, so of course you can use a built-in operation in to check if x in L. So we check x in L is a false, which means 13 is not in the list. But today we are looking at how to implement our own search algorithm using brute force method. So the idea of using brute force methods, okay, so using exhaustive search, okay, is to go through the list, go through our search space, which is the list, and at each iteration, we check if the element is in the list. That is, check whether the element in the list is equals to x. If it is, then you output true and break. At the end of the iteration, that means you have already checked every single element in the list and none of them is equals to x. So we can conclude that x does not exist in this list and hence we can output false. Okay, so implement this. We're going to run an iteration over the list for every element in L. If element is equals to x. If it is, we found it. Okay, so we're gonna create a variable that is initialized to false. The beginning is false until we found it. Okay, so now found is equals to true, and then we break, we stop checking. If the element at this iteration is not equals to x, we go to the next iteration. Okay, now at the end we can print a meaningful message. If found, you just print true. Else, that means it's not found, we just print false. Okay, so in this case, our result is the same as the result using built-in operations. Okay, so the idea of learning exhaustive search is that it gives you the necessary skills to run your own algorithm to search for something, going through iterations. At each iteration, what is it that you want to check for? And if it satisfies what you want to check for, what is the output? If it's not satisfy what you check for, what is the output instead? Okay, so let's look at another example, or rather an exercise, where we are asked to find an element greater than x in a given list. Okay, so you're given a list and you are asked to check if there exists an element that is greater than x. Okay, so this is different from the previous example where you know exactly what you want to find for. You know that the value x is equals to 13 and that is exactly what you want to find. Okay, but here we don't know the element that we want to find. We are looking for an element that is greater than x, whether such an element exists or not. Okay, now in this case, we can't use the built-in method. Okay, because we are looking for an element that's greater than x, not x itself. Okay, but we can solve this easily using the exhaustive search algorithm that we have just described. Okay, so again, we start off with some random list of 500 elements, and each of these elements is in this range here. And we are asking, is there an element in this list that is greater than x, where x is equal to 589? So we can't use built-in operations, but we can use what we have learned before when we implement the search algorithm ourselves using brute force method. That is, we go through our search space, that is our list, and at each iteration, we don't check if the element is equal to x. Rather, we check if the element at the iteration is greater than x. If yes, you output true and break. Okay? You output true and exit. All right? At the end of the iteration, we can conclude that every element that I examined is not greater than x. So there is no such element in the list that is greater than x, and hence we can output false. Okay? So this is something for you to do. So again, we don't know the target value that you are searching for. We only know the property of the target value of the value that you want to search. Okay? The property of the value that you want to search is that it must be greater than x. Okay? So to implement, to solve this problem, again, you use simple strategy as before, except that when you run through every element in L, instead of checking whether they are equal, you check whether element is greater than x. Okay? If it is, file is equal to true, you stop checking, you break. Otherwise, you continue with the next iteration. Okay? So this is for you to complete. Okay? So to do. Right. Now, let's look at a second sample code. That is, we want to find the maximum value of a list. Okay? So suppose again, you are given a list of 500 random values, and each of these random value is taken from this range here. All right? And you are asked to find the maximum value in this list here. Now, if you use in the built-in maximum function, you get that the maximum value is 9,946. Now, again, the whole point of this lab is to help you build the skill of create your own algorithm. So we'll ask you to write your own algorithm to find the maximum value without using the built-in max function. Okay, so let's do the multiple. Let's try multiple versions of creating our own algorithm to find the maximum value in the list. For each of these versions, we're going to analyze the number of iterations that is required and whether it is considered efficient or not informally. Okay, so let's look at version 1. The version 1 is such that since we are looking for the maximum value, all right, and you know that every element is in this range here, so the idea is that we start with the largest possible maximum value. For example, because every element is in this range, so the largest possible maximum value that could occur in L is 9,999. And so we check if 9,999 is in L. If it is, then 9,999 is the maximum value. And then we can stop checking. If not, the next largest possible maximum value will be 9,998. So we check whether 9,998 is in L. If it is, then this is the maximum value. Otherwise, we continue with 9,997 and so on. Okay, so we're basically gonna check one by one, starting from the largest possible value, 9,999, all the way to 0 to see whether it exists in L. Okay, so now our search space is range 0, 10, is the reverse of range 0, 10,000. Okay, so reverse range 0, 10,000 will iterate through. So these, if you set to these, okay, these will give you all the elements from 9,999, okay, all the way down to 0. Okay, so the last element is 0. All right, this won't come out all the way, but it will generate integers starting from 9,999 all the way to 0. Okay, so for each of them, you are going to check if it's in L. If it's in L, then that value will be the maximum. Okay, so we're gonna implement this. Implement version 1, okay, which is we're gonna run for loop over this search space here. Okay, for every element in this search space, okay, this reverse, okay, reverse range 0, 10,000, okay, will generate integers from 9,999, 9,998, and so on all the way to 0. Okay, for each of them, okay, you check if the element is in L. If it is in L, all right, then your maximum value will be the element itself. Okay, so element is the maximum value. All right. If element is not in L, we continue the search. We go to the next possible largest value, which is 9,998, and check whether it's in L again. Okay. All right. So let's run this code. Oh, we forgot to do the break. Once you found it, you should break it because that's the maximum, right? So we say that 9,946 is the maximum value, which is consistent with the results using the built-in max function. Okay, so the idea of version 1 is very simple. We try all possible values. Could it be 9,999? Could it be 9,998? If not, could it be 9,997? And so on. Once you found the value is in L, then you know that that's the maximum that that maximum value. Okay, because the least L is from this range here. Okay, it's not infinite range, but it's range between 0 to 10,000, but not include 10,000 itself. Okay, now let's analyze this version 1 here. What's the number of iterations? So in the worst case, it's going to iterate every element from 0 to 9,999 inclusive. Okay, number of iterations in the worst case is 10,000 because it will iterate from 10,000 to from 9,999 to 0. Actually, it's at most. Okay. So there are 500 elements here, and so there must be some maximum value in these 500 elements here, and each of these value is from this range here. So the number of iterations will be at most 10,000. Okay. In the worst case, okay, because it will iterate from 9,999 to 0. So because L is a random list, okay, which means it could be possible that the number generated is all zeros. In this case, it will have to go through every single element here until it reaches 0 to find the maximum value is 0. Okay, so the number of iteration is at most 10,000. All right, but in each iteration, you run X in L. You run element in L, okay? Okay, and depends on the built-in operation of int. All right, when you run element in L, okay, it really depends how this built-in operator is implemented. Okay, it could be linear. In this, it could be going through every element in list and check whether it is equals to the element, or it could be constant when L is a set, for example. Okay, so the running time of this version depends not just the number of iterations, but also how element in L, which is a built-in operator here, is implemented. All right. If you remember, if list L, if we do element in L, if L is a set, searching over a set takes only constant time, so it becomes efficient. But if L is a list, the built-in operated element in the built-in operations int might take linear time. That means it has to go through every element in L, like what we have done here, okay, to check whether any element is equals to X. All right. So here we just analyze a very informally, where we do a very informal analysis that the number of iteration is 10,000. Now let's try to optimize this code. Okay. Now, can we not run this number of iterations? Okay. So if you can see here, we run 10,000 iterations. All right. But in our list, we only have 500 elements. Okay. So instead of checking the largest possible values and whether this element is in the list, we can, for example, go through every element in the list itself. Okay. In this case, if we go through every element in the list, we will only run 500 iterations. Okay, so how do we do that? So the strategy is that at each iteration, we keep track of the maximum value that the loop has encountered so far. Okay, so you look at the list. Okay, let's print out the list. Okay, so you go through the list. There are 500 elements only. Okay, for each of the elements, you check whether this is the maximum that you have encountered so far. So at the beginning, you've checked with the first element, which is 3131. So since this is the only element that you have seen so far, this will be the maximum value that you have seen so far. And then you go to the second element, okay? And you compare this element with the maximum value that you have seen so far. Since this is bigger than the maximum value that you have seen so far, now you update the maximum the maximum value that you have seen so far to this value. And then you continue. Okay. The idea is that you keep track of the maximum value that you have seen so far at each iteration. Okay. So we create a variable called current max. This will be initialized to the first element in the list. And start with the second element in the list. We compare X with current max. If X is bigger than the current maximum value that you have seen so far, then you update the value. The current maximum value now is equals to X. If no, you do nothing. You continue with the next iteration. Okay? So it's very simple. So we have our list here. Okay. You can try to find the max L, but just to compare your solution with the built-in functions, right? And we're going to create our own iterations, okay? So create our, implement our own algorithm. So implement version 2. Okay, so our implementation version 2 is such that we create a variable called recurrent maximum, and we initialize to the first element in the list, L0. Okay. So the current maximum at the beginning is 5,112. Okay. And then we go to the second element in the list, and compare this value with the current maximum that you have seen so far. If this is bigger, we update it. If not, then the current maximum, which is 5,112, still remain the current maximum. So we don't make an update. We go to the next iteration, which the element is 8,388. And this time, this is bigger than the current maximum. All right, 8,388 is bigger than 5,112. So you update current max to 8388. Okay, so we go through. So starting from the second element, I in range 2 to length of L. Okay, so I is iterating through the indices starting from index 2. Okay, so iterate indices of L starting from index 2. Okay, for every array in range 2 to length of L, what is the element? So you retrieve the I index of L, the element at the I at index I of L. Okay, and you check if the element is greater than current max. If it is, then you know the current maximum has to be updated with the value of elements. Okay, now if current max is equal to elements, you assign the value of element into current max. All right, if not, if it's not greater, we don't make an update. We continue with the next iteration. Okay, so at the end, you can print current max. That will be the maximum value of the list. Now, our implementation of version 2 indicate that the maximum values is 9,997, which is consistent with the result of the built-in function. Okay, so let's analyze version 2. What is the number of iterations? Okay, so here we iterate through at most 500. Okay, so we're starting from 2 all the way to length of L. So length of L is 500, so technically it's 499, but we just look at it as at most 500. Okay, so if you compare between version 1 and version 2, so version 1, you go through 10,000 iterations. Version 2, you go through at most 500. So of course, version 2, it's much more, it has less number of iterations compared to the version 1. So it's much ideal. Okay, so let's look at version 3. So is there a way where we don't have to go through the list and we can still find the maximum value? So if it's possible, that means you don't check every element and somehow you must know where is the maximum value be. Okay, so the idea is L is sorted. Okay, if L is sorted, then how do we find the maximum L? Okay, maximum of L. So say if L is sorted, then we don't have to examine any element in L. Okay, if L is sorted in non-decreasing order, that is from lowest to highest, okay, then the maximum value of L will be just the last element in L. Okay, so let's look at our list here. Okay, right, print L. And if you see here, L is actually not sorted. Okay, so let's look at a sorted version of this list. Okay, L sorted equals to sorted L. And now you print L sorted. Now you see that this list is sorted and it's from lowest to highest. Okay, once the list is sorted, we don't have to go through every element to find the maximum value. All right, we don't have to keep track of the maximum value so far because the list is sorted. You know the maximum value would have to be the highest value in the list that is located at the last element. Okay, then the maximum value equals to L, the last element. Now we know how to retrieve the last element. So index can start from 0 if it's from left to right, or you can start from right to left with -1. So L minus 1, well, square bracket -1 will retrieve the last entry of the list. Okay, so let's print max value. Okay, we also use the built-in function to check. It's 9,997, and we just check. Actually, L sorted. Okay, so L sort, the last entry of L sorted will be the max value, which is consistent with the built-in result. Okay, the result using built-in max functions. All right. So, for analysis of version tree, what is the number of iterations? 0. We don't run any iterations at all because we just retrieve the last value without running any iteration, without checking any element in L. However, note that we actually retrieve L sort, the last entry of L sorted, not L itself. And our list, when we start off, is actually a random list. Okay, chances that it is sorted already is very low. It's not all, and there is a chance that the list generated with random values might not be sorted. Okay, so in order to implement version tree, we actually have to sort the list first. Okay, and sorting is actually very time consuming. All right, it basically requires to go through the list of these elements here and make comparisons. Okay, so the most efficient algorithm that we can use to sort a list of n elements will require n log n steps. Okay, so so in our case, if n is equals to 500, it will require say n equals to 500. So let's do import mat. Okay, let's print what is n times mat.log n. It will require this number of iterations or this number of steps. Require about roughly this number of steps. Okay. So even though we don't run any iterations, but it will still require this number of steps or this number of computations to sort the list. Okay. Now, if you compare to version 2, okay, version 2 require you to examine 500 elements, or in other words, informally require 500 steps. And version 3, because you have to sort the list, okay, even though you run 0 iterations, sorting itself requires this number of steps or this number of computations, okay? So number of iterations is not it's not enough to justify whether an algorithm is efficient or not. You really need to look at the internal steps required to run the algorithm. Version 3 has 0 iterations, but requires this number of steps, which is more than the 500 steps of comparisons in version 2. Now, let's run the experiments on the running time between version 2 and version 3. Version 2 requires 500 iterations, version 3 requires 0 iteration. But we have just mentioned that even though this requires 0 iterations, in version 3, it requires sorting, which is very computational expensive. It requires this number of steps or computational steps, okay? So we can experiment on the running time by using the built-in or Jupyter magic keyword, okay? So let's run this. So I generate a list of 500 elements, okay? And I want to run both versions. version 2, and version 3. Okay, so version 2 is here. All right. So if I put this syntax here in front of my code, it will display the running time of running line 2 to line 7. Okay, so this is the running time. Okay, now let's run our version 3. Okay. So this is our version 3. All right, let's see the running time. Okay, so if you look at here, version 2 have this number of microsecond, and this is version 3. It seems like version 3 is faster, but we need to be very careful here. So it really depends on how large is the number of elements here. Okay, so let's increase L to 10,000. Okay, so now L has 10,000 elements. All right, let's run this again. Let's run this more. Okay, so the larger, the more elements in L, the more we can tell the differences between the running time of version 2 and version 3. Okay, so in version 2, the wall time is 90.8 milliseconds. Okay, and in version 3, it takes 273 milliseconds. All right, so because you have to understand sorting is computationally expensive when for large value of n, you have a large element of L. I mean, if you have large number of lists, okay, it takes longer time to sort, and the most efficient algorithms will take this number of computational steps. All right, so when we have a large number of elements in L, version 3 turns out to take more time than version 2. Okay, now as an exercise, you're gonna repeat all the sample codes from 2A, 2B, 2C, and so on with a different version. Instead of finding maximum value, you're just gonna find minimum value. Okay, and you're gonna go through each of these versions. Okay, version 1, where you look through the search space in the inefficient way, where your search space is the reverse. Oh, it's not the reverse. It's basically the range of 0 to 10,000. Okay, 10,000. Right. So you're looking for a minimum value in a list of 500 elements is generated in this range here. So the lowest possible value is 0. So you check whether 0 is in L. Then 0 is the minimum value. If not, you check whether 1 is in L. If not, if it is, then 1 is in the minimum value. If not, then you continue to check whether 2 is in L, and so on. Okay, and you answer what is the number of iterations. So this is for you to do. Implement version 1. And we all know that this is inefficient. This will require iteration of 10,000 iterations. But as an exercise, I would like you to implement it and examine the number of iterations and sort of to reinforce what you have learned today. And in the version 2, we're going to do it more efficiently, where the strategy is to iterate through the list L itself, which contains only 500 elements. And at each iteration, you keep track of the minimum value that has been encountered so far. Okay, so it's similar as this as a sample code for 2B. Okay, so this is exercise. So instead of keep track of the maximum value that you have seen so far, you're going to keep track of the minimum value that you have seen so far. Okay, so implement version 2. And again, you answer what is the number of iterations. And for version 3, okay, in this version, you are asked to sort the list L and retrieve the minimum value of L using indexing. Okay, So if once you have a sorted list, what is the minimum value? Where can you don't without running iteration, where is the position of the minimum value? And what is the number of iterations? And again, as we have seen before, sorting itself is computationally expensive. Okay, even though you don't run any iterations when you retrieve the minimum value, when you sort the list itself behind the scenes, there is a lot of operations being taken place behind the scenes. All right, so as an exercise, you're going to analyze version 1, 2, 3, which version is more efficient. And you can also use this magic keyword time here for each of the version to find out which has the shortest running time. And again, it's important to know that the running time, all right, depends on the number of elements of L. So the larger number of elements of L, the more indicative, the more the running time display will be more of an indicative of the real running time that compare version 1, 2, and 3. Okay, so this is for exercise. Okay, so this is to do. What's the running time of implementation of version 1 for L above, for this value of L? Okay, and of course, also what's the running time of the implementation of version 2 for L, and what's the running time of implementation of version 3 for L. And ultimately, you should find that version 2 should be more efficient, should have the shorter running time among all the 3 versions. Okay, that's all for today. Thank you.